Hey everybody, welcome to our next video in Unit 12, which is all about the energy that's associated with phase changes. So of course you're familiar with the different phases of matter. So going from a solid to a liquid, or a liquid to a gas, or a solid to a gas, or a gas, whatever it may be. There's a lot of different phase changes that we can have. But there's always an energy change that's associated in each of those. Not only is heat absorbed or released when changing the temperature of a material, there is a significant amount of heat that's absorbed when a material goes through a phase change. So like we talked about with specific heat, it takes so much energy in order to raise or lower the temperature of a material. It takes so much heat in order to do that, heat energy, I should say. However, it also takes a certain amount of energy in order to go through a phase change entirely. So that's what we're talking about in this case. That last equation we used didn't involve any sort of phase changes. It just involved raising or lowering the temperature. So here we're going to talk about those particular phase changes. And if you just look at the three phases of matter, in this case for water, although they all have different temperatures, because of course water melts at 0 degrees, we have to have a higher temperature for water in order to have a gas. But we have to apply a certain amount of energy to that because, of course, we're changing the type of energy that the particles have. Solids have just vibrational energy. Whereas to get something to a liquid, we have to add that translational energy. And it takes a certain amount of energy to be applied to that system in order to add that translational energy to get it to be a liquid. And in the same case, it takes a certain amount of energy that needs to be applied to a liquid in order to add all of that rotational energy to a gas. It takes a lot more energy to go through a phase change than it does to just raise the temperature of something. So that's what we're going to talk about in this particular section. So let's talk about the heat or the enthalpy of fusion. So I am going to use the words heat or enthalpy interchangeably. In any high school class, those two words are interchangeable, which is why I just have them right next to each other. I'm going to say them and they're going to mean one another. However, in the real world, they don't mean the same thing because there's a certain variable that you have to consider, but the variable is always the same for us. So heat and enthalpy mean the same exact thing. And this is the amount of heat that's required to melt 1 gram of a solid at its melting point. I don't know why they call this particular phase change fusion. I guess because when you go from a liquid to a solid, they're kind of fusing together. I don't think that's it. I think there's some other thing that you can use to describe it, but fusion is always going from a solid to a liquid or a liquid to a solid. And the equation you can use to calculate the heat of fusion is this right here. So it looks very similar to Q equals MC delta T, but we don't have that specific heat because, of course, this isn't in here. But there is no change in temperature. And that's because when you are going through a phase change, there actually is no temperature change, which you're going to investigate in a lab that we do in class. So Q, of course, is the heat, which you're familiar with. M is the mass of the sample, and that delta H of fusion is that enthalpy of fusion that's specific to that substance. So here's an example. To melt water, so to melt 1 gram of water at its melting point, 0 degrees, going from solid water to liquid water, you have to apply 334 joules of energy per every 1 gram. So you have to apply or add 335 joules of energy per gram. Because we are adding energy to that system, we say that melting water is an endothermic reaction. And it is endothermic because heat must be applied to the system, because that ice is absorbing all of that energy in order for this phase change to happen. Solids have vibrational energy, but we have to add 335 joules of energy per 1 gram in order to add that translational energy that's needed to make a liquid. Because it's absorbing energy, melting water is an endothermic reaction. Let's consider this in the opposite case. So let's say I have liquid water that is solidifying into solid water or ice. That enthalpy of fusion will be negative. So all that's changing here when I change the sides that these are on, so solid to a liquid, we have to apply energy. So it is positive. The enthalpy of fusion is positive. When I am solidifying water, we have to release energy because it is releasing all of that energy from that translational motion. Therefore, your enthalpy of fusion is negative. So that's the only difference. It's the same value, but again, those semantics matter. When it's absorbing energy, heat is positive. When it's releasing energy, that heat is going to be negative, heat or enthalpy, because again, they mean the same thing for us. So when water freezes, water is an exothermic reaction, and that's because heat's released in order for this phase change to occur. You're going to notice in some of the labs that we do that when you reach the freezing point of a substance, that the thermometer will actually rise. There's a greater temperature as right when you're going through that phase change. And that's because once that material starts to become a solid, it's releasing all of that translational energy. And you can measure that with a thermometer. So you're going to see once you start reaching its freezing point, the temperature is going to go up a little bit because all that energy is coming out of that system. And then it can lower back down again. It's really, really cool to watch or to see how that happens, that you're like, oh my God, like when I freeze this, the temperature's going up. Why is the temperature going up? That's what happens. It's releasing all of that translational energy in the form of heat. Let's go ahead and do the next sample problem together. Sample problem 13. So calculate the energy that's required to melt 55.5 grams of ice at 0 degrees. So notice here we are at ice's melting point. So there is going to be no change in temperature at this point because all of that energy that's being applied to an ice cube as it's melting is going towards the actual melting process, which is something we'll talk about a little bit later in this video. But let's just go ahead and calculate that energy quick. So we know our equation is Q equals M times that enthalpy of fusion right there. And for water, we know that enthalpy of fusion because it's actually given to us in these problems from above. So we are adding energy to the system. So we are going to use that positive value in this case. And again, it's all about semantics when it comes down to this. We have to really get good at understanding whether or not these values are going to be positive or negative. And in this case, we're going to use that positive value because we're melting this. We know we have to add energy to the system. So we're going to use that positive value of that enthalpy of fusion. And that positive value is positive 335. So the mass of the sample is 55.5 grams of water. And I'm going to multiply that by 335 joules per gram. So that enthalpy of fusion is specific to that particular substance at the particular phase change. So you're going to have that either given to you or you could easily find that somewhere when you're solving these problems.
And when you solve for that, in this case, it's very easy, just one multiplication. You get 18,600 joules. And if you want, you could throw that positive in the front, since you will have to apply that to that system. And easy as that. So there's the answer to sample problem 13. Let's go ahead and try a very similar equation with this, but as we're going from a liquid to a gas or vice versa.
So in the same vein, we're going to talk about the heat or enthalpy of vaporization. So it's the same exact concept, except we are going from a liquid to a gas or a gas to a liquid. And of course, depending on the way that you're going is going to be whether or not your value is positive or negative. So this is the amount of heat energy that's required to vaporize 1 gram of a liquid at its boiling point. And the equation is exactly the same. The only difference is that you are going to change whatever this value is, this enthalpy of vaporization, delta H vape, what you're going to hear me call that. And again, let's look at the value for water. So water, to get it to vaporize, it requires 2,260 joules per gram of energy. That is a huge value, which we're going to compare that to other values in class together. So just like we were saying before, when we are vaporizing water, going from a liquid to a gas, that is an endothermic reaction. We have to apply heat to liquid water in order to get it to vaporize. It is absorbing all of that energy in order to gain that needed rotational energy, which is what defines a gas. We need that rotational energy. Whereas if I'm condensing water, that is an exothermic reaction. Heat is going to be released. You're releasing all of that rotational energy in the form of heat in order to go from a gas to a liquid, because liquids don't have that rotational energy. So it's getting rid of it in order to change the states of matter. Let's go ahead and finish this off and do the next sample problem in the notes together.
So let's try sample problem 14. Just like sample problem 13, in fact, it's the same exact equation. The only thing is we have a different enthalpy of vaporization value for that. So that's, again, is specific to that particular phase change. So equation, however, is exactly the same as the previous one. So Q equals M times the enthalpy of vaporization. And I do have to apply that much heat to this. So in this case, because I am going from a liquid, so I'm going from a liquid to a gas, in order to do that, heat plus a liquid gives us a gas. So my value here is going to be positive. So this right here should be positive 1.50 kilojoules. Now, in this case, our enthalpy of vaporization is usually given to us in units of joules. And this particular value gives me the energy that's required for this phase change is in units of kilojoules. So we do have to convert this to units of joules. Remember, there are 1,000 joules in a kilojoule. So I'm just going to move that decimal point over 3 times, and we should get positive 1,500 joules. So now that I know how much heat is applied, so this problem is telling me that we applied 1,500 joules of energy to the system, we want to know how much water can I vaporize using all of that energy. So we're going to solve for mass in this case, especially because it says how much water in grams can be vaporized. Q is positive 1,500 joules. And we're going to solve for mass. And again, normally this value would be given to you, but in this case, because we only talked about water so far, we're just going to use the positive value for the enthalpy of vaporization because we are applying heat to the system. So it requires 2,260 joules per gram of energy. 2,260 joules per gram. And when you solve for that, you should get a mass of 0.66. So you could vaporize 0.66 grams of water if you apply 1,500 joules of energy to that system. So again, I think the hardest part about these is just those positives and negatives, which really that's just takes some practice, unfortunately. Now, what we're going to do in this next part in the notes is we're going to put it all together. And like I mentioned before, you are actually going to be making your own heating curve for a specific substance. I forget what the substance is off the top of my head, but you're going to make something that looks just like this. So as you are heating a substance, and let's say you're starting off far below that substance's melting point. So right here, in this case, we're talking about water. So water, we're starting off at negative 25 degrees Celsius. If I add heat to that system, we can in fact raise the temperature of that particular sample, of that ice. So if I apply heat to that, so right here it's showing that I have an ice cube. I'm warming up that ice, and as heat is being added, so that's what this is down here towards your x-axis, heat's being added. Oops, I did that by accident. Let's draw an arrow going in that direction. I can raise the temperature. Once I reach ice's melting point, however, so notice how we start to get a plateau right here. And as heat is still being applied to this system, notice how the temperature stays the same. And that's because all of that extra energy is going towards melting that ice. So when I have ice right here, look how perfect these molecules are aligned. If you think back to the last unit, or earlier in this unit rather, we talked about hydrogen bonds, and water in particular, when it's in its solid form, has a lot of hydrogen bonds. That's why it forms this very nice looking crystal lattice structure. And once it reaches its melting point, we have to start breaking some of those hydrogen bonds in order for water to gain that translational energy. And that's exactly what's happening here at number 2. So if I look up here at number 2, I have some solid ice. So there's some solid. And I also have some liquid ice on both sides. And all of that added energy is going towards breaking those hydrogen bonds and adding some of that translational energy, because the water needs to be able to take the shape of the container. And it does that with added translational energy. Once that solid is totally melted, so once I've broken every single hydrogen bond in that solid material, well, not all of them, we'll say some of them. I have broken most of them at that point. Now your liquid water is all in the liquid phase, of course. So I have vibrational and translational energy. And you'll notice that once I have all of that solid that's melted, once that phase change is complete, the temperature of water can actually increase again. So notice right here, I can increase the temperature of water. And once we reach its boiling point, look how long this plateau is. Holy moly. So at this particular point, I still have liquid water down here. So this is number 4, we could see. So here's number 4, and there's number 4. This is a really nice image, actually. We have liquid water, and then we have gas towards the top. Even though energy is still being applied to the system, let's just write liquid down here. Look at all that energy that's applied to that. All of that energy is not going towards raising the temperature of that sample. It's going to breaking every single hydrogen bond in that liquid water. Because in order to get something to be a gas, like we talked about in that gas law section, gas particles are very far apart relative to their size. So in order for them to be very far apart, we have to break every single hydrogen bond, and that requires a heck of a lot of energy. which is why this line is super duper long as we progress here. Once, however, I have broken every single hydrogen bond, I can now raise the temperature of that gaseous water sample. So notice here, these particles are really far apart. We have no hydrogen bonds, if of course this was an ideal gas. No hydrogen bonds. And that's because all that energy that was applied was already broken. So there is a very specific rhyme and reason as to why the heating curve for water looks just like this. Now, of course, if we were to construct a cooling curve, it would be the exact opposite of this. So it would start off high and the plateaus would be relatively the same size, but it would just it would decrease as I go across there. So let's go ahead and answer sample problem 15 using this particular image up here. So consider the heating curve for water above. Why does the curve plateau at points 2 and 4, even though heat is still being applied to the system? And like I said, you're going to see this very, very nicely in a lab that you're going to do. So it's plateauing at points 2 and point 4. And why does that happen? And the reason why is because that energy is not going towards raising the temperature. That heat is going towards breaking some of those intermolecular forces to go through that phase change. So let's see here. Why does the curve plateau at points 2 and 4? The heat that is being added is going towards, I don't want to say hydrogen bonds specifically because that's specific for water. I'm just going to say intermolecular forces is going towards breaking intermolecular forces. Sometimes it's very hard to write with this pen. So the heat that's being added is going towards breaking those intermolecular forces, which is why the temperature can't rise because the energy is going to something. And in those two plateaus, it's going towards that actual phase change, which is breaking intermolecular forces. And why is plateau 4 significantly longer than plateau 2? So notice here that plateau 4, it's huge, right? It takes a lot of energy to vaporize water, 2,260 joules per gram, as opposed to melting water, it's 335 joules per gram. Why is that? And like we said up here, so in order to go from a liquid to a gas, we have to break every single intermolecular force to do that. Going from a solid to a liquid, we have to break intermolecular forces, hydrogen bonds specifically, but not all of them because the water molecules are still attracted to one another a little bit as they're in the liquid phase. Actually, for water, it's quite a lot of it because it's water, of course, and they hydrogen bond very strongly. But we have to break every single hydrogen bond to vaporize the sample. So plateau 4 is longer than plateau 2 because every intermolecular force must be broken to vaporize the sample. And remember, that's because gas particles are far apart. Gas particles are far apart. And the last question, do lines 1, 3, and 5 have the same slope? So what does that say about the specific heat capacity for each phase of water? So we're comparing now the slopes of lines 1, 3, and 5 because they're not the same. And we can compare the specific heats capacities for each phase of water just by looking at the slope. Notice how the slope for 5 is very, very steep. And that means that it doesn't take a lot of energy to raise the sample or to raise the temperature of a gas for water. It's actually very easy to vaporize. So the specific heat must be very, very low. Doesn't require a lot of energy. Not a lot of energy required. Whereas for liquid water, for example, this is not entirely flat, but it's not nearly as steep as section 5 is. So it does require quite a bit more heat to raise the temperature of liquid water. So in this case, because this line is not as steep as number 5, it requires more energy. Requires more energy to raise the temp. So we can compare the specific heat just by looking at those slopes. So liquid water must have the highest specific heat capacity because it requires the most energy to raise the temperature of that. Whereas gaseous water or water vapor has the lowest specific heat capacity. It does not require that much energy to raise the temperature of gaseous water. So do lines 1, 3, and 5 have the same slope? No. What does that say about the specific heat capacity for each phase of matter? So of course that means that they're different. So I'll put a little arrow here, and just because this pen's giving me a hard time. So they are different. And how can you tell which phase has the largest specific heat capacity? So the largest specific heat capacity would be for liquid water. And that's because the slope of the line is the lowest, or we'll say least steep. Requires more energy to raise the temperature of liquid water. So by constructing a heating curve, you can actually learn a lot about a sample. And if you decide to take AP chemistry, you're going to see quite a bit of questions on heating and cooling curves like that. This is also important to understanding that you have 2 phases of matter during that actual melting process and during the vaporization or condensation process. There's 2 states of matter that are present, and you can draw those by representing them appropriately. So solids, of course, are going to not take the shape of their container. Liquids do take the shape of their container, whereas gases are far apart. They take up the entire volume of the container. And we do have a generic heating curve with equations. So as you are doing each of these types of problems, as you're doing determining the energy required to raise the temperature of something and to go through a phase change, we can use those equations that we already talked about. So if I am raising the temperature of a solid, so this right here, this is another heating curve. So I'm at a solid at this point. I can raise the temperature of a solid. And in order to find out how much energy is required to do that, I can use the equation Q equals MC delta T, where the specific heat is for that of the solid material. When I start to go through the melting process, so this must be for water because of course we have melting point at 0 degrees and boiling point at 100. When ice is melting or water is freezing, I don't have a change in temperature. Therefore, we have to use the equation Q equals M times the enthalpy of fusion. And we can't have a delta T in there because there is no change in temperature. Once we progress through that melting process, and when all of my sample has melted, now I can the temperature can rise again. And when I am determining how much energy is required to raise the temperature of a liquid, I'm going to use Q equals M, C delta T, but my specific heat capacity must be for the liquid in that case. So notice the difference, solid and liquid there. Once all of my sample has been reached to its boiling point, I can then boil that material. But in order to find how much energy is required to boil, I have to use this other equation. So Q equals M times the enthalpy of vaporization, another constant for water, for anything really. And notice that this line is much longer than the one below it. That's because it requires a lot more energy to boil off that water. We have to break all of those hydrogen bonds. And once all of my sample has vaporized, I can then raise the temperature of that gas by using the equation Q equals MC for a gas, delta T. So as you are doing these types of problems, you have to keep this in mind right here. And it's very tedious because you have to consider what's happening. Am I raising the temperature of something? Is it going through a phase change? What are the constants in each of those instances? And you'll be given each of those values if you need them. So using that, let's go ahead and try sample problem 16. So calculate the energy that's required to change a 15-gram sample of water from 85 to steam at 113 degrees. So we are going through a phase change in this case. And in order to do this type of problem, we need 3 steps. So since we're at 85 degrees, I'm somewhere right about around here. We first have to raise the temperature of that liquid to its boiling point, and then we have to boil it, and then we have to raise the temperature of the vapor. So this is a 3-step problem in this case. So we're going to say here, this is 3 steps. And the first step would be to heat the water, heat to its boiling point. And it's not at its boiling point yet, so we're going to bring it to 100 degrees. And we're going to do that using Q equals MC delta T. Mass of the sample is 15 grams, that we know. Specific heat capacity for liquid water is 4.184 joules per gram, degrees Celsius. Oops, forgot that. And my final temperature is 100 degrees because that's the temperature that water boils at. And my initial is 85. So I'm raising the temperature 15 degrees. And when I solve for that, I get 941 joules positive because I have to apply that much. Now that step has only brought water to its boiling point. So now we have to actually go through that phase change. We have to vaporize the water. Vaporize water. And to do that, we're going to use the equation Q equals M times the enthalpy of vaporization. Mass of the sample is still 15 grams. And the enthalpy of vaporization for water is 2,260 joules per gram. That's a constant. You don't have to memorize those because I'll give them to you, whatever ones you need. And when you solve for that, you get 33,900 joules positive because I'm applying that much. However, I'm not done. So at that point, I've just gotten all of that sample of water from 85 degrees, and now it's all a gas, but it's still at 100 degrees. Now I have to raise it to 113. So step 3 would be to heat the vapor. Heat the vapor. And because I could heat the vapor, I'm going to use Q equals MC delta T again. Mass is still 15 grams. The specific heat capacity for gaseous water, water vapor, is 1.87. And my final temperature is 113 degrees. And my initial is 100, since I'm raising it from 100 degrees. And when you solve for that, you get 365 joules. Positive. So in order to find the total amount of energy, of course, you would have to add all of these together. So that 941 joules that was needed to heat the water to its boiling point, and the 33,900 joules that was required to then vaporize that sample, and the 365 joules of energy that was required to heat the vapor. If you add all of those up, you would get a total of 35,206 joules of energy, positive, would have to be applied to the system. So the total energy is equal to that. And we just add all of those together. Like I said, these can get a little tedious sometimes, I understand, but this is a very important concept in thermodynamics. You have to understand when to use each of those different equations. And I think using this might be able to help you as you progress through this. Let's just dive in and do that last sample problem together. So how much heat is needed to melt 25 grams of copper that is at 82.5 degrees Celsius? The melting point of copper is 1083 degrees Celsius, and it gives us all the constants there that we need. So how much heat is needed to melt? So I not only have to bring copper to its melting point, but then I have to actually melt it. So this particular problem, sample problem 17, is a two-step problem, 2 steps. And the first step would be to heat to its melting point. So because I'm heating something to its melting point, we do have a change in temperature. So I'm going to use the equation Q equals MC delta T. Mass of the copper is 25 grams. Specific heat capacity for solid copper, that's that 0.385, 0.385 joules per gram degrees Celsius. And final minus initial for delta T. So your final temperature is 1083. And that's because that's the temperature that it starts to melt at. So 1083 degrees Celsius. And my initial temperature is that 82.5. 2.5 degrees Celsius. And when you solve for that, you should get 9,600 joules must be applied. Now that we're at the melting point, we have to actually melt it. So you do have to get some practice with understanding what the problem is asking you. So because it's saying to melt, we want to actually liquefy this material. So let's go ahead and actually melt the substance. And we're going to use that using Q equals M times the enthalpy of fusion. Mass is still 25 grams, and that enthalpy of fusion was given to us. That's that 134 joules per gram. And you solve for that, you get 3,400. Notice how it doesn't require nearly as much energy for this one, and that's because copper is a metallic substance. It has all those metallic bonds, delocalized electrons. It's very easy to raise the temperature of copper and to melt copper. So all I have to do next is add them up. So 9,600 plus that 3,400 gives us an answer of 13,000 joules. And if you want to be specific, you could do a plus since you are adding energy to this system. Thermodynamics is tough, I'm not going to lie. It takes a lot of practice. So I think I have a couple of labs that we're going to do for you to see some of this stuff in action. I think that's really the one way that you can get very good at this is by seeing it. And also, you just have to do lots of problems with this. I didn't truly understand thermodynamics, I think, until I started teaching it for AP chemistry. And that's because I had to sit down and I had to really internalize what all of this information meant. So if you have any questions, please don't hesitate to ask me because I know it can be overwhelming. But that's what I'm here for. So don't hesitate to come and see me when you're doing practice problems in class to ask those questions because I'm sure I have had all of those questions before. Make some notes in your notes for anything specific. And otherwise, I will see you in the next unit. Actually, we're chugging through right along here. So I hope you have a wonderful day and I'll see you soon. Bye.